Okay, can people hear me in the back? Let's get started. Welcome back to CS 198, 126, Deep Learning for Visual Data. And today we will go through the final deep learning lecture so we can get started on actual computer vision starting Wednesday. Before I delve into this lecture, I do have some announcements to make. Quiz 1 is due tonight. This quiz covers concepts from the previous 3 lectures. Everything that you need to answer questions on the quiz should be in those lecture slides. If you do need to revisit them, they're on the website. We have also released Quiz 2. Quiz 2 is going to cover concepts from today's lecture and Wednesday's lecture on convolutions. It's going to be due next Monday, so it's a little while for that. Homework 1 was also released this weekend. I'm really sorry for the delay. Setting up the Grayscale autograder took a while. Since this homework was delayed, I have extended the due date to next Wednesday from this Friday. And hopefully, if you do have to use office hours, you can attend, this week or the Wednesday before the homework's due. Speaking of office hours, we have OH. We started OH last week on Wednesday 4 to 5 in Corey 531 and Friday 4 to 5 in Corey 212. Yeah, I guess we can delve into today's lecture. In the last 2 lectures, we looked at deep learning from a more mechanical perspective. Like we learned about what a neural network is, how it's actually implemented under the hood, and how you actually optimize it. Today, we are going to focus more on some intuition behind what deep learning is actually doing. So it's not going to be as mechanical or as mathematical, but it's going to be more focused on, I guess, like high-level details and intuition. Before we delve into deep learning, let's take a step back and think about classical machine learning. What is the machine learning problem? So assume that you have a data set of XY pairs, and your goal is to predict this label Y from an input X. But the way you typically do it is you extract some sort of features from your X, and then you pass these features into a machine learning model, which can be parameterized by parameters theta, for example. Right? So if you were to look at a more concrete example, if your goal is to predict housing prices from a house, and this is a very real application of machine learning in the real world. Companies like Zillow have these models running right now. Something that you might do is you cannot pass in a house directly into a machine learning model, but you can extract information about that house, and this can be things like the number of bedrooms in that house, the size of the house. I've not included this in this table down below, but maybe the median income of the neighborhood that your house is in. And it doesn't even have to be numerical data. You can also include like categorical data, like, does the house have a pool or not? It can be like a true or false value. But the idea is that you can extract different kinds of information and pass this information as a proxy or a representation of your input to this machine learning model. And your goal at the end is to learn some sort of parameters theta that take in this input and produce some output Y. And in fact, you can actually break this down into a 2-step process. You take your raw input, you extract some features from that input, and you pass these features along into your actual ML algorithm where you try to learn these parameters theta. Does this setup make sense to everyone? Yeah, let's move on. So this is how machine learning was done in like the old days. People would come up with like different kinds of feature extractors, and And they would usually like hand program these from scratch because different problems might require different sets of features. If your data was pretty simple, like it was arranged in a table, these feature extractors would be pretty easy to program because you can just take a single column or a single row of that table and you'll be done. But what if you have something more complex, like an image? How do you extract features from an image? And there are multiple kinds of features you can extract. You can find out information about all the edges in that image. So this feature extractor is called HOG. It's called histogram-oriented gradients. We won't talk about this in this class, but it was historically pretty important. Or you could even extract information about corners or something called key points. So the idea is that these extractors there's like a huge variety of extractors that you can use. But in each case, you're still hand programming these from scratch and taking the output of these extractors, these features, and passing that into your actual ML model. Now, in the Intro to Machine Learning lecture, we talked about how these models have parameters that can be learned from the data. That's all well and good, but you have to keep in mind that we are only learning half of the pipeline from data to prediction. And in this process, we are still hand programming these feature extractors from scratch. We need to ask ourselves if we can make this whole pipeline learnable. So instead of just learning the weights of your ML algorithm, can you also learn these feature extractors themselves? And deep learning says you can. In fact, deep learning says you can learn the entire pipeline from end to end. So you can have learned feature extractors, that take in some sort of image and, produce some learned feature representation of that image that can then be passed into another learned, algorithm like a neural network. But what if instead of keeping these two processes separate, you just combine them into a single process, right? And that's basically what a neural network is. A neural network can take in an input and directly go to an output and it will take care of all this feature extraction process by itself. You don't have to hand program anything. You just make the single model that will act on your data from the get-go and just like process it in any way it needs to. In fact, this is also why we called deep learning representation learning, because you're allowing your model to learn all the representations that it feels it needs to solve the task at hand. You essentially just say that, hey, I'm going to relinquish all the control to this neural network and let it learn whatever it feels is necessary. I'm not going to intervene by any means. I'm not going to hand program anything except the network itself. And sort of that's it. Oh yeah, sort of on a side note, features and representations sort of mean the same thing in ML. So if you do go to some other resources and you see these two different terms, just know that they mean the same thing. Now, a neural network is just a stack of layers, which means if you treat each layer as something that can yield a learned representation, then each neural network is nothing more than just a stack of learnable representations, right? And in fact, the representations at later layers depend on the representations learned at earlier layers, right? Because if you were to look at this whole diagram of a neural network, the activations from a previous layer are used as the input to the next layer, right? So whatever the neural network learns in, say, layers 1 and 2, the output of that is then passed in as the input to layer 3, and then layer 4, and on and on. So since later representations depend on earlier representations, we call these representations hierarchical in the sense that there's like a clear hierarchy forming. Earlier layers tend to learn, more low-level features. Like, if you were to take an image, this can be things like corners or edge information or color information, while later layers try to learn something more abstract. And we will see an example of this in a few slides. So this part doesn't make sense just quite yet, don't worry about it. Before I move on, does anyone have any questions about this whole idea of what a representation is and what deep learning is actually doing? If there are no questions, then I guess I'll move on. The second part of this lecture is sort of the meat of this lecture. It's transfer learning. And let's sort of motivate that from the beginning. Training a network from scratch is hard. It takes a lot of time. It takes a lot of compute, your GPUs, your TPUs, whatever. And it also requires a lot of training data. And typically, the more data you have, the better models you can learn, because data diversity helps a lot with the training. It prevents overfitting and allows your model to generalize better. But more than that, you need money to train these models, right? If you don't have money to burn, how would you even how would you even buy GPUs or TPUs, right? If you can't even afford them. And this sort of limits the scope of model training to these few big companies, right? So, your huge LLMs that are being pumped out right now, they're only coming from a few select labs in the country, right? Like Google Brain, OpenAI, Facebook AI Research, for example. And a common person can't really use them, can't really train them from scratch. Let's think about how a model is actually trained. When we train a model from scratch, and we sort of saw this in the last lecture, we initialize its parameters randomly, and then update them through some sort of optimization algorithm like stochastic gradient descent, RMS prop, Atom, whatever algorithm you want to use. And we repeat this process for whatever task you want to solve. Like if you want to train a model for object detection or classification or image generation, doesn't really matter. You start from the same process every single time, right? But we need to think if we really have to. Do we really have to start from scratch every time when we train a model? If you were to take humans as examples, like even us students at UC Berkeley, think of the 61 series. You come in as a freshman, you take 61A, you learn how to program in Python, you learn about variables, functions, loops, if statements, classes, etc., etc. And then when you move on to 61B and you program in Java, you don't really learn everything from scratch, do you? You already know what these different programming paradigms are. You know what a variable is. You know what a loop is. You already have some base knowledge that you can adapt to the new task at hand, which in the case of 61B is learning data structures. And this kind of also holds for 61C, when you learn about C or assembly, you already know what a loop is. You know what a if statement is. You don't have to learn all of this from scratch, right? We want to see if we can apply this concept to neural networks as well. So if we were to imagine training two separate networks for, say, cat dog classification or face recognition, we would go through this whole training from scratch process. This neural network that we would use would have to learn this suitable set of feature extractors for whatever inputs that we are passing in to these models, right? And like I mentioned earlier, these representations that the network learns are hierarchical. What this means is that lower layers of this network might focus on learning very concrete details, like the kinds of shapes or edges or textures or patterns that are present in an image, whereas higher level layers that are more deeper into the network might try to learn something more abstract that can be formed by combining these low-level features into something more complex. So in the case of cat dog classification, it might learn this mental model of what a cat looks like or what a dog looks like, right? So notice how these low-level features are kind of general enough to be extracted from any kind of image, right? If I were to pass in an image of a car or of any animal or of a building, doesn't really matter, right? All of those images will have, edges, patterns, textures that would have to be extracted before we can build on to more abstract concepts, right? And these abstract concepts, like these high-level representations, only start to diverge in the later layers, right? So we can kind of guess that the lower level layers of a network are going to stay kind of similar across all the different networks you can train. Now, how these feature extractors actually work in practice, don't worry about that yet. That will be covered in the upcoming lectures. You will learn about this network called a CNN, or a convolutional neural network, that uses these extractors called convolutional layers to extract different kinds of representations from an input. And here is, I guess, a more concrete example. So this is a network that's already been trained for image classification on some data set like ImageNet, right? If you were to look at, say, layers 1 and 2, well, what this picture is trying to show you is what kind of image patches is each layer looking for. If you were to look at some of the lower level layers, you can clearly see that these layers are trying to look for specific patterns, right? Or specific textures or specific edges. But the later layers are trying to look for more complete objects. So instead of looking for different kinds of stripes, this later layer is trying to look at complete human faces at that same time, or whole pictures of flowers at the same time, right? So this kind of gives credibility to the whole idea that lower level layers are trying to learn more concrete low-level details, while deeper layers are trying to learn more high-level concepts. Does anyone have any questions about this whole idea of different kinds of features and how there's sort of a hierarchy between them, where these higher level features depend on the lower level features, right? So if you want to learn what a dog looks like, you have to combine features from the first two layers into something bigger to produce this mental concept of a dog, right?
We're still working off the same framework where it's like the weights from earlier have a bigger meaning later. Like, we're not introducing. Does layer 5 use the same weights as layer 1?
No, so these are completely different layers. So we took some 5-layer network, trained it for image classification, and we let these layers update through something like gradient descent. So the model decided that this is what layer 5 should be, then this is what layer 1 should be. They don't have to be the same. And in fact, it would make sense if they're not the same, right? Because you want layer 5 to learn something else than layer 1, because the inputs that layer 5 takes in depends on the outputs of the previous layers, right? So it wouldn't really make sense to just keep learning the same layer again and again, because it might not produce a meaningful output at the end.
So in earlier slides, we would have like a basic representation where weight 1 goes to x1, weight 2 goes to x2, weight 3 goes to x3, but x3 also gets the output of x2 and x1. Are we introducing new weights at layer 5, or is it just the same weights that begin at layer 1 and are run through all 5 layers?
So each layer has its own set of weights, right? So if you were to look at this, there's like input that we designed in lecture 2. And we'll repeat this process. All the different layers we want to include, right? So what this is saying is we have some input layer that connects to all the neurons from hidden layer. We've taken this input, we produce some output, which is then used as the input to this other hidden layer, right? Okay. And we keep repeating this process for all the layers that we have.
All right, perfect. And we're not introducing new weights, like the input, the output of the last layer is the input of the new layer.
Right, yeah.
Like additional weights.
It's exactly the same as what you learned last week.
Perfect, thank you.
So if you want to share information or like the knowledge gain between two networks, how can we do that? It's like, what are we really sharing between two networks, right? If you think back to it, neural networks are nothing more than just stacks of layers. So you can just share the layers between two different networks, right? We can say that, oh, some of these layers in this pre-trained network have learned what I need to solve this different task. What if I just borrow these layers at the get-go and just try to modify them in some way? And there are two ways in which you can sort of approach this sort of problem. One way is something called a frozen feature extractor. So what we do is we take this network that has already been trained on some task one using some data set one. Because it has already been trained, we call this network a pre-trained network. You might have seen this term in ML literature out there, but yeah, that's what it really means. It just means a network that has already been trained in some way. What we do is we freeze some of the layers. We make it so that they cannot be updated anymore, in the sense that any gradient updates to them are completely disabled. We will not compute a gradient with respect to them if we want to do a backprop operation in the future. They're completely frozen. They will never be changed. And we discard the remaining layers. So you can treat these fixed frozen layers as sort of a feature extractor, right? You pass in this input, and you can take the output of these frozen layers as a representation of your input, right? Because a representation is simply just any way of presenting that input to a neural network, right? So we can take this intermediate, we can take the intermediate activations from these frozen layers and pass it into a different network. Now the layers for this new network are going to be trainable, and they can be updated through gradient descent. This is sort of an aside, but in computer vision literature, if the new network that you're training is just single layer, this whole process is also called linear probing. This part is not important, but just in case you see this term out there, right? Now we take the intermediate activations from the frozen layers, pass it into this new network, and train just the new network on our new data set. This allows you to transfer some of the information that was learned by network one to network two, essentially. Does anyone have any questions about this process? Yeah.
So what you said about, sometimes when you replace the only, basically the final layer, I've always wondered about that. Like, why do they do that? Like, wouldn't it be probably better to replace a couple layers with one? Like, can you sometimes get better performance with only replacing the final layer?
So the number of layers that you have to replace is basically a hyperparameter. I don't think there's like a single right answer. You have to sort of experiment with it and see what.
But there are scenarios where you get better performance, or is it purely just for I guess to reduce costs?
That's one reason why you just replace the final layer. There are scenarios where replacing multiple layers would be helpful, and I'll sort of get to that in a minute. Yeah.
The two networks, the old one and the new one, have to be pretty similar, right? You can't just swap out stuff that works on any random data. I'm assuming it needs to be from the same data set, training set.
So the data set depends on the task that you're working with. So network one was trained on dataset one for some task one, right? What we are doing is we're taking some layers from network one and using that as sort of a backbone for network two that is going to be trained on dataset two for some task two down the line.
Okay. But again, they do have to be the same job, right? The same network, same job or task.
Kind of, but not really. We will talk about different kinds of pre-trained networks in a way later lecture, but in practice, the tasks that you do select tend to be pretty similar. So for example, you might pre-train a network on some image classification task, and you might use the layers from that network for let's say, an object detection task, which are pretty similar in what they're trying to achieve, right? So in practice, the two tasks that you might use might end up looking similar, but it doesn't have to be.
Thank you.
Yeah. The other approach is something called fine-tuning. So you sort of start with the same setup, but instead of discarding these non-frozen layers, what you do is you just start training them with those starting weights. So you allow gradient updates from your new data set back into the model, and you update these non-frozen layers with gradient descent and whatever optimizer you want to use. You can optionally also add like more custom layers on top of like these non-frozen layers. Like this whole process, like of how many frozen layers you want, how many non-frozen layers you want, and how many custom layers you want is like this. It's basically a big hyperparameter that you have to sort of tune based on whatever you're trying to achieve. But yeah, the idea is that you don't have to throw away these layers. You can just update them further. In fact, sorry.
Yeah, I had a question. What's the difference between custom layers and not custom layers?
So the non-frozen layers are pre-trained layers. Custom layers are layers that you add that are randomly initialized. Yes, in fact, you might imagine just not freezing any layers at all, and you might imagine just like fine-tuning the whole network from the get-go. And in some cases, you might actually want to do that. We will get to some examples and again a later lecture. But when you're fine-tuning the whole network, you can kind of view this process as training a network from scratch, but instead of randomly initializing the network's weights, you initialize it to some set of pre-trained weights, right? So if you were to look at our optimization perspective, that was a few slides ago, where we start with randomly initialized weights and update these weights through some optimizer. Starting with pre-trained weights is essentially giving you a head start. So you're saying that instead of choosing any sets of weights, I'm going to choose some that I think are going to be good enough for the task that I'm trying to achieve right now. Yeah, and in a sense, you can just view pre-trained networks as sort of giving you a head start in the new optimization process for the new task that you're training this network for. Now, how do you choose if you want to fine-tune or just use like frozen layers? There are two considerations that you have to keep in mind. So you already have this network that was trained on task 1, and you're trying to train a new network for task 2. You have to look at how similar the data set for task 2 is to task 1 data set and how big it is, right? If the data sets are kind of similar and the task data set is big enough, then it should be okay to fine-tune the whole network. But if the task data set is very small, then just don't fine-tune. You freeze the whole network and just train a single linear layer. So just do the whole linear probing process that I sort of mentioned earlier. On the other hand, if the task 1 and task 2 data sets are vastly different, then you should probably fine-tune the whole network, because it's possible that network 1 didn't really learn any knowledge that's going to be useful for task 2, because the data sets are so different. But on the other hand, and this is sort of the least favorable case, is when your data sets are very different and your new data set is very small. Again, just don't fine-tune, because if you fine-tune with a small data set, you might just overfit the network to the training data set, and just try to train some sort of like custom layers on top of the frozen layers from network 1. Again, this is not like some hard and fast rules. This is just some general guidelines that you can follow when you're trying to do transfer learning. And you'll actually do transfer learning in homework 2. Any questions before I move on? Yeah.
So what is task 1 and task 2? Can you give like an example of like?
Yeah, so task 1 is what you trained your first network on, and task 2 is some other task that you're trying to train a network for. So your goal is to somehow use the network trained for task 1. Your goal is to somehow leverage that network for task 2. So because this network has already been trained, it might possess some knowledge that might be useful for the second task. You're trying to essentially find a way to leverage that knowledge.
Let's favor a case. So when you have like a very different data set with very small text, data set, like should we expect like the final accuracy or the variance to be very high? Because basically those two networks are very different.
It could be, it might not be. It really depends on what you're using for your task 1 data set, right? So imagine if your task 1 data set was on cat.classification and your task 2 data set is like something to do with medical imaging, like MRIs or X-rays, not X-rays. Yeah. You can see that those data sets are very, very different, but you might still leverage some information that was learned in the cat.classification data set, which was, these lower level features, right? Because even if you were to train a new network on MRIs, you still need to extract information about, say, edges, right? And the cat.classification network possibly learn to do that. So you can still leverage it, but there are no guarantees if it will, yield any improvements than training the second network from scratch.
So does that mean like if two tags have any correlations, we can just do the transfer training on them?
You might try it. In general, it doesn't hurt to try transfer learning. Transfer learning is actually pretty big in computer vision. So, and especially if you look at the field of object detection, transfer learning is almost always in an object detection, where you transfer the features learned from some classification network for some detection network. Yeah, so we're going to take a small aside and talk about some deep learning terminology that I think is kind of useful to know. And you might see this, in papers, blog posts, articles, whatever. So in deep learning, we call a shot the number of new examples that you show to a pre-trained network during transfer learning. So a few shot training, in few shot training, you show this pre-trained network very few new examples from dataset 2. In k-shot training, you show exactly k examples from dataset 2. Similarly, in 1-shot and 0-shot, you either show just one example from your new dataset, or in 0-shot, you don't show any examples from the new dataset, right? And if you were to sort of look back at a frozen feature extractor example, that's kind of what it's doing, right? So if you were to look at a bunch of frozen layers, you don't update them anymore because, whatever examples you show, these sort of frozen layers, they'll just stay set in stone forever. Those are not going to update. Another example is LLMs. If you look at GPT-4, you never really fine-tune GPT-4, right? You just sort of use it from the get-go, like the way it's provided to you by OpenAI. So this is another example of zero-shot learning, because you can specify some examples in your prompt to GPT-4, and it will just sort of learn what it has to output just based on prior knowledge and just that, no other new information. Another topic is that of embeddings. So an embedding, at least in deep learning, is just some map that maps from some discrete or continuous space to a continuous space. For example, this map can take in things like images, text tokens, audio samples, and produce a vector that is some representation of those different inputs, right? So in a sense, an embedding is just some way to represent non-numerical data in a numerical format. This example that I have up here is embeddings of the titles of different books, right? And something that's really cool that pops out is if you were to look at embeddings from similar, like genres, they tend to cluster together, which kind of makes sense, right? So embeddings have this property that they can map semantically similar objects to vectors that are close together in this new continuous space. Now, how do you even obtain these embeddings in the first place? You're talking about deep learning, you just learn them. neural networks already learn their parameters via some gradient-based optimization process. What if we just use it to also learn embeddings, right? Or instead of learning embeddings from scratch, what if you just take a pre-trained network and use the intermediate activations from that network as an embedding? So if you were to go back to that whole frozen feature extractor example, you can look at the outputs of just the frozen layers as an embedding of your input, right? Because your input, whatever, it can be text, images, whatever you pass in, is going to be compressed down to some vector. That's what that activation is, right? Yeah, so you can essentially convert pre-trained networks into learned embeddings. And you can use these for like different kinds of tasks. One example is this MNIST classification task that you will encounter on homework 1. This is the task where you're trying to classify images of handwritten digits from like 0 to 9 to like what digit it actually is. And imagine that you're training this network where you take in, this image flattened out to a vector, and you try to predict what digit it actually is, right? And you might say that we have this intermediate layer that only has 3 neurons, right? What if once this network has been fully trained, I look at the outputs of this intermediate layer for the different inputs that I pass in, or this intermediate layer can also be 2 neurons, but what if I just look at the embeddings that I learned from this pre-training and plot them in some way? And you might see that your model has learned embeddings that are actually meaningful in some way, right? So if you look at the right plot, embeddings of digits that are the same are clustered close together. And sort of the same goes for if you were to use a 3-dimensional embedding. What this is showing is that learned embeddings are pretty useful because they don't just learn any kinds of vectors. They learn vectors, they learn this like new space that has meaning. And in fact, this space is also called the latent space. So if you look back at this image, if you look back at this example, where we look at images of digits, these images are high dimensional, right? So these images can be, say, 28 by 28 pixels, which means each image has 784 numbers in it. But we just saw that we can represent these huge vectors with just 2 or 3 dimensions, and that's good enough. This low dimensional structure that's sort of prevalent in this high dimensional space of your original data is called is captured by this thing called a latent space. And in other words, these latents are nothing more than just low dimensional representations of your original data. Now, why do we care about latent spaces? Well, first of all, it's easier to work in low dimensions, right? You don't want to work in high dimensions because that can lead to something called curse of dimensionality. If this is a term you have heard, that's fine. If you have not, don't worry about it. But it typically means that high dimensions are not good, low dimensions are easier to work with. Another place where you might see them is when we talk about generative modeling. So when we talk about these models like GANs, VAEs, diffusion models that try to generate images from scratch, this whole concept of latent spaces is going to pop up there again. So we will go more in depth into it later. I just wanted to show this concept just once in class. So I guess let's go back to transfer learning. We're done with our aside. We learned about how we can use pre-trained networks and leverage their features for new tasks. Let's think about why we want to do this. So if you pre-train a network on a huge data set, and this network itself is very big, it turns out that the representations it learns tend to be very generalizable and useful, right? And this makes sense. Bigger data set means more diverse data. It means the model has seen more examples. It has a bigger and better worldview of the kinds of images that are out there. And small networks, small data sets struggle to develop these representations by themselves. So we might want to leverage huge pre-trained networks to help to facilitate the training of these smaller networks. Another reason is that these huge pre-trained networks tend to be available off the shelf. So like if you were to Google something like Meta's Llama model, you can just download it from GitHub and just start using it right away, right? Or if you were to look at another example from NLP, these learn embeddings called Word2Vec or Glove are also available online that you can then leverage for different kinds of NLP tasks. Or even in computer vision, we tend to pre-train huge models on the ImageNet dataset, which ImageNet is just a huge dataset with 1.3 million images. And you can find these models online, right? You can also think about it from a more practical perspective. So, embeddings capture this low-dimensional structure of your original input in the low-dimensional vector, right? And if you work with these low-dimensional representations, you might free up a lot of space. So imagine that you have a 256 by 256 by 3 image, which has roughly 200,000 pixels, but it's possible to get just a 2048 dimensional embedding of that image. If you were to use just this embedding, you can notice that there is a very huge reduction in space or of memory that you would need to train this new network, right? Yeah, so using lower dimensional embeddings can speed up your training and also make the whole training process much easier. So, just a small recap. Transfer learning in a nutshell is simply, just yoinking other people's work and using it to facilitate the training of your own model. All of the examples that we have seen so far were sort of from the computer vision world, but transfer learning is a more general concept that can be applied to essentially any kind of networking machine learning. Transfer learning is actually big in NLP, right? You might see people fine-tuning Llama or GPT models out there. And finally, there are two ways of performing transfer learning. You could treat your pre-trained network as like a frozen feature extractor, or you could fine-tune it. Before I move on, any questions about transfer learning? Yeah.
For transfer learning, we take like word uploader, and when you have new data, you have like to train the new data, or just like use the pre-trained data to predict like the outcome.
So we take pre-trained networks, but we either fine-tune them or use them as frozen feature extractors to train a neural network on the new data. So we don't have access to the pre-trained data. We only have access to the pre-trained network. So the new tasks that we are trying to leverage these networks for have their own data sets that we want to use. Take GPT, for example. I know I keep coming back to this, but it's like a very popular example. You don't really have the data that OpenAI trained GPT on, right? But you can still leverage GPT on your own data sets that you provided. Yeah, so let's talk a bit about unsupervised learning. I know we sort of touched on this topic in the intro to ML lecture, but in supervised learning, if you were to look at the whole process that we went through last week, we talked about how we define these loss functions that take any model's predictions and the ground truth labels, and you're trying to optimize this loss, you're trying to minimize it, right? Since this loss function is dependent on the labels that you take in a sense, these labels are supervising the training of your network. In unsupervised learning, you don't receive any supervision from labels. You pretend that the labels are not there, and you just try to learn something useful from the data itself. Some examples of unsupervised learning, if you have taken something like 16B or EX127, you might have seen PCA. Another example is clustering, right? So if you have like a bunch of data points, you can try to create like multiple clusters within them that might be present naturally, but you don't really use any labels to create these clusters. So why do I bring up unsupervised learning? I just mentioned that pre-training huge models on huge data sets can lead to really good representations. But it turns out that these huge data sets tend to be unlabeled, right? you can get big labeled data sets, but that's also sort of limiting the scope of what you can do, right? So we know that this ImageNet data set, which is already huge, has 1.3 million images. But it could be possible to train on even more images that are out there on the internet, right? The internet has like billions of images and not just millions. Same goes for something like NLP. You could pre-train a model on something like Wikipedia, but that's only like, say, billions of tokens, billions of words, whereas the whole internet has trillions of words, right? So the idea is that you can use these huge data sets, but it's possible that they might not be labeled, they might not have any structure at all. So if you can find a way to leverage them, so if you want to leverage them in some way, you kind of have to resort to unsupervised techniques because they can function without labels, right? And labels, while they're nice to have collecting them is a huge hassle, right? Because labeling each image can be very tedious. It requires manual labor, requires time. If you were to look at these huge models that OpenAI trains, they literally have like contractors that they pay where humans label their data sets for multiple hours at a time, and they have to, pay them some sort of like contracting fee and everything. So this can be very expensive. Also, it's also hard to come across labels if you're looking at very specific domains, right? So if you're looking at medical data or legal data, it's possible that you might not get access to labels because it might be something confidential. So unsupervised learning can be pretty useful. And the aspect of unsupervised learning that we're going to focus on in this class is self-supervised learning. So you don't have labels, but what if you can artificially create labels from your data itself? And turns out this technique is called self-supervised learning, right? Because the labels that you created from the data itself, which means that data is supervising its own training, or self-supervised learning. Now, one very general technique in which this can be applied is you take your data, you hide some part of it, and you ask your model to predict the hidden part from the unhidden part. So you can use the hidden part as the label and the unhidden part as your actual input. And you can train different kinds of models using this paradigm. And we're going to see some examples of those in the next, in the remaining 5 minutes. Before I jump into them, I do want to go over some terminology. So in the whole transfer learning section, I've been referring to, a task 1 and a task 2. Turns out that in the case of SSL or self-supervised learning, these tasks have a name. So the task on which you pre-train a network is also called a pretext task. And the task in which you use these pre-trained features is called a downstream task. So if I go back to my example of pre-training on a classification data set, I would call this task of image classification as a pretext task. And leveraging those features for object detection, I would call object detection the downstream task. And there are many kinds of downstream tasks that you can use. Computer vision, you have classification, object detection, segmentation, even image generation. In NLP, you can use pre-trained features for something like machine translation, document summarization, question answering. Even in RL, you could take a pre-trained policy and then fine-tune it model-free in your environment. So let's actually look at an example of a self-supervised network. This model is called an autoencoder. And what this does, or rather what it looks like is that it has 2 parts. So there is an encoder and a decoder network. The encoder network takes in some data, and the output of this encoder network is a very small vector. So it essentially compresses this data into a very small vector that the decoder network then takes in as input, and it tries to reconstruct the original data back, right? So if you were to train your autoencoder network, where you take in some input and you have to reconstruct that input back from just its compressed representation, you're trying to learn some information about the input, right? So in a sense, you're forcing this middle part, this which is also called the bottleneck because it's like a very small vector, right? You're forcing this bottleneck to only extract information that it would consider relevant for this reconstruction down the line. So instead of just capturing everything about your input, you're only learning the most important parts of your input. And this compressed representation can then be used for different kinds of downstream tasks down the line. Another example is this model called a ROTNet. Oh, right. Sorry, I went over time, but there's the QR code for lecture attendance. I will try to get this sorted out. What I'll do for now is just excuse attendance for everyone for this lecture, because I did not plan on it being deactivated. Because I guess my lecture is technically over, but I will still continue to go through the remaining slides. It should take about 5 minutes. Yeah, if you look back at this model called the ROTNet, what this does is it takes your image, it randomly rotates it by some amount of degrees, like 90, 180, 270, or 0 degrees. And the goal of this model is to predict what the rotation angle was, right? So in this case, you might view this rotation angle as some hidden information. And your goal is to predict this hidden information from the unhidden part, which is the rotated image, right? And the hope is that by trying to predict rotation angles, your model will learn about the relationship between high-level features and low-level patterns in an image. And I think this image sort of demonstrates that concept. So the figure on the right shows the features that are learned from a fully supervised model. And you can see that when you pass in some sort of input, the model is concentrating on like different parts of the image at once. But if you were to look at the features from the self-supervised ROTNet model, it's trying to focus on the object as a whole at the same time. So I think this image of this dog in the middle row, third column demonstrate this perfectly. You're looking at the body of the dog and its head at the same time. But if you were to just use the features from this fully supervised network, the model is only going to be focusing on just a single body part. So ROTNet forces your model to learn about spatial relationships between different components of your image. There is another similar self-supervised task you can construct. It's called jigsaw puzzle. You take an image, you divide it into a 3x3 grid. You sort of shuffle this grid, and your model has to learn a way to sort of unscramble this this grid back together into the original image, like sort of like a jigsaw puzzle. Yeah.
If it's not supervised, how does it know if it's like learning?
So you define what the labeling scheme should be. So in the case of this rotation prediction task, you take your data set of images, you randomly rotate each image by the angle specified, and then you designate the label as the angle that you rotated it by. So you are deciding what's correct and what's not. You're making these labels on your own.
So it's gonna like make 4 different buckets and then you'll just choose this one with 90, this one with 100.
Sure, yeah. So yeah, you are designating these labels yourself, so you get to choose what's correct and what's not. Yeah. You have this whole jigsaw puzzle unshuffling task. I don't think this is too important. I'm going to get into more important examples. This whole technique is applicable more generally to other fields of ML as well. If you look at NLP, I name dropped this thing called Word2Vec a few slides ago. Word2Vec is essentially a way to generate embeddings for text tokens. One way you can do this is you can take some sentence and you can try to predict the words surrounding a given word in that sentence, right? So one way of doing this is something called the continuous bag of words model, in which you take the sentence like the dog bit the man, and you try to predict the words dog and the from the word bit. or you can sort of invert that whole concept altogether, and you can try to predict the word bit from the words dog and the. So this whole idea of trying to predict some unhidden part of your input from some hidden, you're trying to predict some hidden part of your input from some unhidden part extends more generally to other fields as well. One big example in NLP is something called masked language models. So instead of just predicting, a word from the immediately surrounding context, what if you try to predict, multiple words in a sentence from the whole sentence as a context, right? So you take in the sentence like a quick brown fox jumps over the lazy dog, you hide some of the words in that sentence, and you pass the unhidden part into a network, which then has to try to predict the hidden words, right? And this is a self-supervised task because you're designating what the labels are, which is the hidden words, and you know what your input is. In fact, if you have heard of this model called BERT, that's exactly what it's doing. It tries to reconstruct what the masked words are in a sentence from the unmasked words, and it does some other stuff, but that's sort of the main deal. The reason I bring up BERT is because we're going to talk about another model called an MAE in the self-supervised lecture, which is a few months from now. But it's a computer vision model that takes inspiration from this NLP model. So that's why I have it up here. Yeah, that's what I have for today. I'm sorry for going over time. I'll try to make the next lectures more contained. Oh yeah, any questions about any of this? Oh yeah, sure. Yeah, if you have any questions, you can sort of like come down and ask.